Hi everybody, we're going to be covering lesson 1.5 in geometry today, and this section is on triangles. So first thing that we're going to look at again is the objectives, and our objectives here are to be able to define, classify, and identify triangles based on how they're marked or measured or their parts. So there's quite a few that we're going to go through. But before we get started on the triangles, we have to make sure that we have a general assumption of all of the standard type things for geometry. So when we assume something, we're assuming that it is, or we're accepting that it is true without having to prove it to be true. So there's some pretty standard things that we are going to say or assume to be true. Because otherwise we'd have to always come up with proofs and facts that these things are in fact concrete or correct in our definitions. So the first thing for geometry is that when you draw a line, it is going to be straight. The second thing we can assume is that when you have two lines crisscrossing or intersecting, they're not going to bend back around and intersect again. So they're only crossing once. All right, the third thing is if you do have a line, all the points that are on that line are collinear, meaning they're all going in that same direction. And then the same idea there is if you have points on a plane, they're all coplanar unless they specifically state otherwise. All right, now there are things that we cannot assume as well. So we cannot just say, yeah, that's true, just because of how it looks. So the first one is going to be that if you see two lines that they look parallel, you cannot just say that they are because they look parallel. They have to have markings proving that they're parallel. So I cannot assume lines are O-A-R-E parallel. But must have marks. The next one is similar to parallel. You cannot assume that lines are crossing at a 90-degree angle or are perpendicular unless there are markings to prove that. And the third thing that we cannot assume is that two figures that look the same are congruent. They have to have all of the documentation showing that they are the same. Okay, so lines are straight and crossing lines only cross once. And if points are on a line, they're on the line, they're all going the same direction, they're collinear. And if they're on a plane, they're all on the same plane, they're coplanar. All right, let's get to those triangles. So a lot of these are ones that you've seen before, and because we talked about angles on the last lesson, These are exactly the same definition as the angles, except it's a closed figure making a triangle. So a right triangle is when you have exactly one 90-degree angle in the triangle. And remember, a 90-degree angle can be represented with this little box in the corner, or you could physically write 90 degrees. But it has exactly one right angle. An acute triangle has 3 acute angles. So again, we can't just assume something. So when I draw a triangle here, it looks like all 3 of these are acute angles, but I can't assume that. And so I'm going to have to put in some values or some more information stating that all 3 of these are less than 90 degrees. So remember, less than 90 degrees. All right, now this next piece of information is possibly something new. Triangle corners, they have to add up to 180. And so if I am going to put in numbers in here, I want to make sure that my 3 numbers add up to 180 degrees. That is something we'll learn down the road as well, but just so that I can have documentation here. So maybe I'll do 60 degrees here, 50 degrees here, and 70 degrees here. So if I were to add all those up, I would get a total of 180 degrees. You could also just label the corners and then say the measure of angle A is less than 90 degrees. The measure of angle B is less than 90 degrees. Measure of angle C is less than 90 degrees. And I know it gets a little confusing with the angle symbol and the less than symbol. Okay, obtuse triangle. Again, we have a triangle, but this time we have one angle that is obtuse, or larger than 90. But smaller than 180. So again, I want to make sure that I'm emphasizing that one corner and not just visually looking obtuse, but I want to have some documentation. So I'm going to put in the number 100 because that is a number between 90 and 180 degrees. Again, you could mark it as a corner and you could say the measure of angle C is, let's see, less than 180, but greater than 90. Okay, here are some triangles that might be new names for you. Scalene, scalene triangle. This is a triangle with no equal or congruent sides. So all the sides are different lengths. All right, now again, I can draw it to look like they're all different. But I have to have proof. So I would have to have 3 measurements that are all different in length, or I could use hash marks showing that this double hash mark is a different length than this triple hash mark, which is a different length than this 4 hash marks here. So this is a scalene triangle. All right, equilateral triangle. We actually already looked at this when we had equilateral. That means that the side lengths were all equal. So this is a triangle with all equal or congruent sides. So we did this on a polygon, but this works for triangles as well. If the triangle is a polygon. Now, my picture doesn't look like all 3 sides are perfectly equal. However, as long as I put documentation in, they are going to be assumed equal. So since each of these sides has the same marks, all 3 sides are the same length. All right, the next one is an isosceles triangle. In an isosceles triangle, it's a little bit different because it's not a specific number. It says at least 2 equal sides. So that technically means that this equilateral triangle is an isosceles triangle because it does at least have 2 equal sides. So all equilateral triangles are considered isosceles, but they don't have to have 3 equal sides. So I'm just going to draw a quick sketch here, a triangle with 2 sides that are marked equal, but it could also be all 3 sides. Okay, now for the isosceles triangle, because it's a fancier triangle, we do have some specific names that we put with it. So for this isosceles triangle, I'm going to mark these 2 sides as the same length. And then the side down here that is not the same length, it could be if it was an isosceles triangle, but it doesn't have to be. This is going to be considered the base. And when we have the base, it is connecting 2 angles, and those are called our base angles. So this one right here and this one right here, those are base angles. And then between the 2 legs that are congruent, that angle up on the top here, that's called the vertex angle, which is kind of silly because all corners are considered to be a vertex. But on an isosceles triangle, we need to distinguish the difference between which one is the vertex and which ones are the base angles. All right, now we're going to just do a quick recap here. And this is kind of reviewing the material from the previous lessons, but it does tie into what we talked about for the triangles. So this one, number 1 here, what type of angle is shown? So because of this 90-degree mark, I know that this is a right angle. All right, question number 2 and 3, those ones don't actually have real specific measurements like they should, and we cannot make assumptions. So I'm going to throw in some numbers here. So let's say that this one was 20 degrees and this one was 120 degrees. So based on those numbers, 20-degree angle, that is an angle that is less than 90 degrees. So this would be an acute angle. And number 3, 120 degrees is greater than 90 degrees, but less than 180. So this is an obtuse angle. All right, question 4. This one has actually 2 different terms that go with it. So right here you can see that I have angle 1 on the left and angle 2 on the right, and they're both sharing a vertex, and they're both sharing a side of their angle. So these 2 are actually forming a linear pair. However, because a linear pair creates this straight line, and straight lines are a total of 180 degrees, it is also considered a supplementary pair. Now on this page, there is another pair of supplementary angles. They total 180 degrees. So that would be down here in question number 7. If I add these 2 together, 60 and 120, it does come out to be 180 degrees. So this is another supplementary pair, but it is not a linear pair because it is not sharing a vertex. They have separate corners, and they are not sharing a side to form a line. Okay, going to number 5 here. On number 5, here I can see I have angle 1 on the left, and I have angle 2 on the right. and they both share a vertex, but their sides are not overlapping. So remember, this is called a pair of vertical angles. Now you might say, well, they're not going up and down, and vertical means up and down. For geometry, remember, that's a different definition. So here, these two angles are the vertical angles. Okay, number 6, it's a lot like number 7, where I have two separate angles. If I total these together, though, 20 plus 70, that makes 90 degrees. And 90 degrees are complementary angles. Whoops. All right, number 8, write down the names of the congruent triangles. Here we have triangle ABC. We need to say what triangle is equal or congruent to triangle ABC. So what I like to do is I like to color code things that match up. So here I can see a single hash mark along this side here. And if I look at the other triangle, I see that same single hash mark over here. On the original triangle, there's a triple hash mark at the bottom. And over here, I see a triple hash mark on the side. Then the final one is a double hash mark, and I see that down at the bottom here. So now that they're color-coded, I can go through and look at the pattern following the letters A, B, C. So if I start at A and I go over to B, that's going across the blue section first, and then B to C, that's the order of the letters here, that's going across the green section, and then closing off the triangle goes over to pink. So I want to follow blue, green, pink when I write down the name of this next triangle. So blue is here, green is here, and pink is here. So I want to start up at the top and go blue to green to pink. And so that would be the letters F, D, E. So even though ABC is in alphabetical order, you can see that this triangle is not, and it's based on where the congruent markings are. All right, number 9, a concave pentagon. So concave means it's like caved in, and when we connect all the diagonals, there's going to be at least one on the outside. Pentagon is a 5-sided figure. So if I draw a convex pentagon, this is convex, that's the typical one that we see. So I want to take one of these corners and like poke it in so that it's caving in. So if I take this top corner and I pull it down into the shape, I still have my 5 sides, but now it is concave. So both of these are pentagons, but this one is concave. And again, that's because if I were to connect all of the diagonals, at least one of them would be on the outside. All right, question 10. Sketch and label a regular quadrilateral. A lot of times the word regular gets overlooked, but that is a geometric term. Quadrilateral, remember, is like a square, a rectangle, a kite. Those have 4 sides. But remember, regular means they're equilateral and equiangular. And so equilateral means all of the sides need to be the same length. Equiangular means all of the angles are the same measure. So I need 4 sides. And that does not look like a perfect straight lines, but remember, in our assumptions, if we are drawing these, lines are straight. To be equilateral, I'm going to put hash marks in all of the all of the sides to show that all sides are the same length. And then to be equiangular, I need to put hash marks in the corners showing that all the corners are the same measure. Now, if you're thinking, well, if all the corners are the same measure, wouldn't they all have to be 90 degrees? In a quadrilateral, yes. So another option for this picture would be to draw all the sides the same and 90-degree angles in the corner. But you don't use the 90-degree angles for every equiangular picture. It's just because it's a quadrilateral. And quadrilaterals have to total 360 degrees. So if I did 90, 90, 90, and 90, that would get me the total of 360. But this is also an acceptable way of showing equilateral and equiangular in a quadrilateral. All right, here's our summary. So we will use this to recap this information at a later time.